Organic Chemistry 1, such a fun class. Learning about spectroscopy. Okay, so section 14.3, we're going to talk even more about wave number here. And it says that the frequency or wave number for a stretching vibration depends on a couple of things. The wave number depends on bond strength, and it depends on the mass difference of the atoms. If we think about bond strength. Let me just think about it in terms of general chemistry 1, what you would have learned there. Like, let's say you have a carbon-carbon, single bond that you'd find in an alkane, and then you go to a carbon-carbon double bond that you would find in an alkene, and then a carbon-carbon triple bond that you would find in an alkyne. Well, hopefully you remember that a triple bond is going to be the strongest carbon-carbon bond, and then a carbon-carbon single bond would be the weakest. And so we see bond strength affecting wave number. So take a look at this. It says here that we have this really neat formula for wave number, and you do not have to memorize this formula. You do have to memorize 2 parts of it, and I'll show you what they are. So it says wave number is equal to 1 over 2 pi times the speed of light. Okay, everybody should know what pi is. Everybody should know what the speed of light is. But then it's multiplied by the square root. So power to a half is the same thing as the square root of F over m reduced. So RED stands for reduced or reduced mass. So F, what is F? F means the force constant. Again, if you've studied physics and you've studied Hooke's law, F is equal to kx. The spring constant K is analogous to F here, which is the force constant. So if force constant, which is bond strength, is in the numerator, what does that mean? We see that wave number is directly proportional to force constant. I mean, it's the square root of the force constant. But the bottom line is if the bond strength or force constant is in the numerator, the stronger the bond, the higher the stretching frequency is going to be, the higher the wave number. Okay, the weaker the bond, then the lower the stretching frequency. So that means if you were to compare the stretching frequencies of carbon-carbon single bonds, carbon-carbon double to carbon-carbon triple, it means that a carbon-carbon triple bond is going to have an absorbance at a higher wave number than a carbon-carbon single bond. Now, what the heck is this m reduced in the denominator? Well, reduced mass is this here. You take the masses of the atoms in the bond. Okay, you take M1 times M2. So let's imagine you have a carbon-hydrogen bond, for example. Okay, what we do is we take the mass of a carbon, which is about 12. So this is about 12 AMU. And then you have the mass of a hydrogen, which is about 1 AMU. So reduced mass, M reduced, would be 12 times 1 divided by 12 plus 1. So that would be 12 over 13. And when you get 12 divided by 13, you end up with 0.923. I added an extra sig fig here, but whatever. Okay, so that's how you calculate reduced mass. So what does that tell you? It tells you that the smaller your atoms are in your bond, the higher the stretching frequency is, and that the larger the atoms are, then the lower the stretching frequency is going to be. Okay, let's say you had a carbon-oxygen bond. If you had a carbon-oxygen bond, well, carbon has a mass of 12 and oxygen is about 16. So if we take 12 times 16 and then we divide that by 28, okay, then we get the reduced mass for a carbon-oxygen bond is 6.86 approximately. And it's a bigger number and it's in the denominator, and so it's going to stretch at a lower frequency. So small atoms have a higher stretching frequency. And those are the 2 main take-home messages from that slide. Here's just some examples proving that. The trends in stretching frequency of given bonds can be rationalized based on, again, bond strength, which is our F, okay, and mass difference, which is our M reduced. Well, let's take a look at some examples. So in number 1, what are we comparing? We're comparing the masses of atoms. All of these are bonds between carbon and different atoms. As you go from a hydrogen to a deuterium to an oxygen to a chlorine, the masses of the atoms get heavier and heavier. Remember, reduced mass is in the denominator, and so as the atoms get heavier, the wave number for the absorption frequency gets smaller and smaller. Conversely, if we talk about bond strength, as you go from a triple to a double to a single, what happens is the wave number decreases because a stronger bond has a higher force constant or bond strength, and that is in the numerator. Give me a thumbs up if you follow me on the rationale. Again, you don't have to memorize the entire formula. There's going to be no math on the quiz, like calculate the reduced mass or anything, calculate the wave number. It's understanding the rationale. The force constant is in the numerator and reduced mass is in the denominator. Cool. There we go. Pretty cool, huh? Well, what do we look for? What do we see when we look at an infrared spectrum? Well, it says here that the wave number formula and empirical observations allow us to designate specific regions representing specific types of bonds in the infrared spectrum. Since we started out talking about bond strength, let's take a look at that first. If you look at single bonds and compare them to double and triple, what did I say? Stronger bond absorbs at a higher wave number. And we see that as we go from single bonds to double to triple bonds. Single bonds usually absorb lower than 1,600 reciprocal centimeters. Double bonds are somewhere between 1,600 and 1,850. And triple bonds are above 2,100, but below 2,300, generally speaking. Now, if you're wondering, well, Mr. Dion, I thought you said that single bonds, and this is a single bond, I thought you said those are supposed to be down here. Well, I said it doesn't just depend on bond strength. It also depends on the masses of the atoms, right? For this trend that you see here, it depended on the force constant. Mr. Dion needs more coffee, I think. However, this trend that you see here, bonds to hydrogen, this is dependent on the reduced mass, right? Since hydrogen is so small, it only has an atomic mass of 1 AMU. Well, that's why if you have a bond to hydrogen, it absorbs at a really high wave number. Again, just because it's so tiny, right? Hydrogen is such a tiny element. All right, and there we go. Well, let's see here. What's some other things we can do when we see an infrared spectrum? What's the first thing you could do? Well, in Chemistry 3101, we're mostly interested in absorptions that occur above 1,500 reciprocal centimeters. We call this the diagnostic region. This region provides very clear information about bonds, the types of bonds, the bond strengths, etc. Below 1,500 reciprocal centimeters, we call this the fingerprint region. We might go in there once in a while, but we're going to stay out of there a lot of the time because the fingerprint region is a lot more difficult to analyze. So if you're thinking, well, then it can't be important, it's not true, because if you compare the spectra of two compounds that are similar, oftentimes the only way to distinguish between them is by looking at the fingerprint region, right? Only by looking at the fingerprint region, which again, we don't do a whole lot of. In Chemistry 3101, we spend most of our time up here in the diagnostic region. But let me show you an example of how the fingerprint region would be useful. Check this out. This is two alcohols. This is called 2-butanol, and this is called 2-propanol. If you look at these two compounds and you look at their infrared spectra, they're pretty similar above 1,500. Let me just show you. If I draw a line here at 1,500 and I draw a line here, that's not the most vertical line out there, is it? Probably make it a little bit better, like this maybe? I don't know. But if you look above 1,500, they look pretty darn similar, don't they? Okay, and I know there's tiny little differences, like you see this here, there's nothing there. But, you know, if you look, it's got a really broad absorbance here. They both have the same absorbances here. And they even have some like little absorbances around this area. So they're pretty close to the same in the diagnostic region. But if you look at the fingerprint region, wow, they're very different, aren't they? Very, very different. I mean, the first thing that my eye is drawn to is this really strong absorption around 1,000. It's not here. If you look, you see a very strong absorption here around 800 reciprocal centimeters. It's not here either. You're probably noticing that there's a really strong absorption here. I mean, there's a little one here, but it's not nearly as strong. So there's a lot more differences in the fingerprint region. And thus, if we were doing, you know, advanced infrared spectroscopy, the only way that you would be able to distinguish between these two molecules using infrared spectra would be looking at the fingerprint region. But again, in Chemistry 3101, we don't look at the fingerprint region a whole lot, so don't really worry about it. You know, going back to the whole idea of bond strength, I want to show you something really cool, really neat, a way that you can distinguish between an sp3 hybridized carbon-hydrogen bond that you might find in an alkane, for example, with an sp2 hybridized carbon-hydrogen bond that you might find in an alkene. So this is some kind of alkene, or it doesn't have to be an alkene. There's other functional groups it could be, but anyhow, that's neither here nor there. Or a carbon-hydrogen bond between an sp hybridized carbon and the hydrogen. And what you see is that they all have different absorption frequencies. Is that cool or what? Because now we have something in the diagnostic region, 29, 31, 3,300 reciprocal centimeters, and we can differentiate between the hybridization of the carbon that is bound to the hydrogen. Now, if you're wondering, well, how can these bonds be different? They're all just carbon-hydrogen single bonds. Well, obviously, it's got something to do with the hybridization of the carbon. And the good news is that we looked at chapter 4 only a few days ago. And so I'm sure that you all remember when we were talking about the hybridization. Oops, well, I'll just back up. I thought I had a picture of the orbitals, so I'll just review with you. Is that as you go from sp3 to sp2 to sp, remember that the orbitals get smaller? Now, if the orbitals get smaller, what does that mean? It means that the bond strength increases. So it gets stronger as you go from an sp3 to an sp2 hybridized carbon-hydrogen bond. And the strongest one of all is going to be the sp hybridized carbon-hydrogen bond. Why? Because an sp hybridized orbital is smaller than an sp2 or an sp3. And so what do we see here? The stronger the carbon-hydrogen bond, the higher the stretching frequency. And this is pretty dang cool. Why? Because if you look in the diagnostic region, you're able to differentiate between an alkane, an alkene, and alkyne just by looking for certain stretching frequencies. Check it out. If we draw a line at 3,000 reciprocal centimeters on each of these spectra here, and they're just showing a small portion of it, but look at the alkane. It has nothing above 3,000, but you see it's got a bunch of stretching here below 3,000, around 2,900. Well, that's what it says right here, around 2,900 reciprocal centimeters for sp3 hybridized carbon-hydrogen bonding. Whereas we go to an sp2 hybridized carbon-hydrogen bond, so this carbon is sp2 hybridized, we see that we get an absorbance right at 3,100, or right around 3,100. Check it out. It says here around 3,100. And then for the alkyne, we should see something around 3,300. Let's check it out. Check this out. At the alkyne, you go 3,000, 32. So this would be around 33, maybe around here. Look at that. Boom. And so we're able to distinguish between these different carbon-hydrogen bonds with different hybridizations of carbon just by looking at the diagnostic region, just by looking at a small portion of it, between 2,900 to 3,300 reciprocal centimeters. Very, very cool. Give me a thumbs up if you follow me on that. Are there any questions on that? Of course, we're going to look at examples of it. I'm still kind of going through not the motions, going through just the background. All right, now, if you're looking at this slide and saying, hot dog, this is going to be great. I'm going to love IR because I'm going to be able to look for this signal, and then I'm going to know I have an alkene. I'm going to be able to look for this signal, and I know I've got an alkyne. Well, I have some good news and some bad news. The good news is we'll look at many examples where you can apply this rationale, but we'll see some where you can't apply that rationale. Let me show you why you can't always hitch your wagon to that. The reason why is if you have an alkene, but it's tetrasubstituted, meaning it has just R groups on all of the vinylic positions, then you have no carbon-hydrogen stretching between an sp2 hybridized carbon and a hydrogen. So even though it's an alkene, you see no signal at 3,100. Conversely, if you have an alkyne that's disubstituted, well, there's no sp hybridized carbon-hydrogen bond. Therefore, you don't see a signal at 3,300. Now, again, that's not something we run into a ton of in this class, but it could happen. So just because you don't see the signal doesn't mean it's not there, right? This just goes back to the whole axiom that we know in science, which is you can't prove by a negative, you can't use a negative proof. Just because it's not there doesn't mean it doesn't exist. All right. Well, let's talk about resonance. Your buddy resonance. We covered this in chapter 2. So you can see why we bring, chapter 14 right after chapter 4, because in chapter 2 we talked about resonance. We also talked about bond strength in the hydrocarbons chapter when we talked about alkanes and cycloalkanes, and now we're kind of bringing some of those concepts into this chapter. Well, do you remember resonance and how it just represents the delocalization of electrons when we draw different resonance structures? Well, let me tell you how resonance can affect the wave number of a stretching signal. Check this out. If you look at a ketone, and this is something that you don't have to necessarily memorize for the quiz, because I'm going to give you that handout that has the different absorption frequencies on it. But if I give you a ketone generally absorbs somewhere around 1720 reciprocal centimeters. However, if you have a conjugated ketone, and conjugated just means that the bonds alternate double, single, double. That's all that means. And then they keep alternating double, single, double, single, double, single. So you have a double, a single, and a double. So we call that a conjugated ketone. Well, check this out. It absorbs at a lower wave number, lower frequency, lower energy. Why would that be? Well, it can't be any difference between the reduced mass, because both of these have the same atoms in the carbon-oxygen bond of the carbonyl. It must have something to do with bond strength. So bond strength or F. It's got something to do with the bond strength. Well, check this out. If you look at a ketone, there's only one resonance structure that we can draw for the ketone. Remember, there's a difference in electronegativity between these two atoms, and there's a pi bond, so we can draw this resonance structure. However, with a conjugated ketone, there's one more resonance structure that you can draw, because you can draw the first one, but then you end up with an allylic carbocation. And so what that means is that if you look at these two resonance structures, you see that the bond has double bond character and some single bond character. However, if you look at the conjugated ketone, it's got double, but it's also got twice as much single bond character. We know that single bonds are weaker than double bonds. So if this has more single bond character, it means that the carbonyl, check this out, it means that the carbonyl in the conjugated ketone is a weaker bond. We could just put here weaker, we'll put here stronger. It's not a huge difference, but just because this is a weaker bond, it absorbs at a lower frequency, and thus it absorbs at a lower wave number. So conjugated carbonyls always have lower stretching frequencies. We see the same thing that we saw with ketones with esters. An ester, generally speaking, the carbonyl has an absorbance somewhere around 1740. And when you have a conjugated ester, it has a lower absorbance for the exact same reason, because you can draw an extra resonance structure that you cannot draw with the ester. Pretty cool, huh? I stop recording.